Hello, St. John's 7th graders for the 2020 to 2021 school year. This is the final installment of our summer videos, and this video is going to focus mostly on geometry, although we're going to see how some algebra relates to that geometry, which is always cool. And we're going to talk about mostly area. There'll be a little bit of perimeter in there, but in the chapter 6 of our 7th grade textbook, that chapter concerns the area of rectangles, parallelograms, triangles, and later trapezoids. We're not going to deal with trapezoids this summer. We'll wait till we get to it later. Also in that chapter 6 are the circle formulas for both circumference, which is perimeter, and area. And those circle formulas, of course, involve that famous number you've probably heard of, the number pi. But we're not going to deal with circles until we're actually into the school year. So let's look at some formulas. I've used some lowercase script letters here, which is sometimes the tradition with line segments. Often in geometry, line segments are represented by lowercase letters and points are represented by capital letters. That's not always consistent, but that's kind of a rule that some people follow. What I have over here is the area of a parallelogram. I tried to make a little sketch of a parallelogram here. The area of a rectangle, the area of a square, and finally the area of a triangle. That's what, on the left side, the capital A stands for area. The area of a parallelogram is the base times the height. We're going to talk about that. We'll talk about these concepts of base and height, but one important thing to keep in mind that I'll say right now is that a base and a height always meet at right angles. In other words, they are perpendicular to each other. This little symbol here, for obvious reasons, two little line segments that are perpendicular means the base is perpendicular to the height or forms a right angle, a 90-degree angle. Next, we have the area of a rectangle. The area of a rectangle is usually given as length times width, but the length and width of a rectangle could also be called its base and height. A rectangle is a special kind of parallelogram. Because a rectangle is a parallelogram, the formula for the parallelogram base times height has to also work for the rectangle. But by tradition, more often we call the two sides that have the different lengths on the rectangle the length and the width. Next, we move to the square. Now, a square is a rectangle, and therefore it's also a parallelogram. It is the most special kind of quadrilateral, the most special kind of four-sided polygon that we can have, where all four sides are the same length and all four angles are right angles. A square is a special rectangle, a rectangle is a special parallelogram. Now we can give the formula for the area of a square as s squared. There's a tradition to call each side of the square s, one letter, because all sides are the same length. But you can see two of those sides that meet at right angles in a square as base and height, or the length and width. We don't usually describe the sides that way because they're all the same length, but you can think of the area of a square as length times width because it's a rectangle, but you'd have to understand that the length and width are equal, which makes it a square. And the same thing with base and height. So area of a square, s times s, base times height, length times width. S times s, of course, is abbreviated s squared, and that's why the exponent of 2 is called squared, because it gives us the area of a square with that length side. And finally, this is kind of cool, the area of any triangle can be thought of as half the area of a parallelogram. Any triangle can be thought of as half of a parallelogram. So the area of a triangle is 1/2 times the base times the height. Just go back to the parallelogram formula, and we'll talk about why a triangle is half of a parallelogram. 1/2 times base times height, of course, is equivalent to base times height divided by 2. So this is sort of a roadmap of where we're headed in this video. But first, we'll pause a little bit to talk about some algebraic notation. I'd like you to consider 2x, 3x. This is 2 times a number. This is 3 times the same number. 2 times x plus 3 times x, and then I'd like us to consider 2 times x times 3 times x. Now these are completely different. This is a lesson that I have been giving for years. I always choose 2x and 3x, keep them kind of simple. This is an area that young students such as yourselves, just beginning the road of down the road of algebra, where there's often confusion. Please try to keep straight the concept of addition and the totally different concept of multiplication. These two operations are approached completely different. 2x plus 3x, I'll tell you, is 5x. And if you look at that, you know, it might seem intuitive. It might seem, well, that's what it's supposed to be. But let's talk about why. The distributive property can explain why 2x plus 3x is 5x. Because we can represent 2x plus 3x like this. 2 plus 3 in parentheses times x, right? If you look at what I just wrote here and you apply the distributive property, multiplying x by 2 and then adding 3 times x. 2 times x plus 3 times x. The distributive property works for all numbers, and this, what I wrote here on this line, is exactly equivalent to what's above. But of course, 2 plus 3 is 5. That's why 2x plus 3x is 5x. There's an even more basic way to think of it that even maybe a third grader could kind of relate to. A third grader learns that 2 times x is x plus x, or x plus x is 2 times x. And the 3 times x, a third grader knows that 3 times x is x plus x plus x. And then we've got that plus sign in the middle. So what do we have? 2x is added together plus 3x is added together. Altogether, that's 5x is added together, which the third grader knows is 5 times x, 5x. Now this down here is completely different. It does not depend upon the distributive property. In fact, if you try to think of the distributive property here, it won't help you. You'll make a mistake perhaps. Think of 2x times 3x as 4 numbers being multiplied together. In math and algebra going forward, we often think of this 2x as a single number, and it is. Like up here, this is the number 2x. It's a single number. It's made up of 2 times x, but down here we really want to think of 4 numbers being multiplied together. And the associative and commutative properties of multiplication allow us to write a series of numbers multiplied together any way we want, any order, any grouping. Just try that for yourself. You know, if you have to do 2 times 3 times 4 times 5, you can rearrange those 4 numbers any way you want and always get the same result. So let's think of the 2x times 3x as 2 times 3 times x times x, because that is what it is. 2 times 3 is 6. We can simplify there. And we have an abbreviation for x times x. The abbreviation for x times x is, of course, x squared. So please notice, I'm circling the 2 answers here. Kind of my pen slipped a little bit here, but you can still see it. Notice the 2 entirely different answers. When we add 2x and 3x, we get 5x because of the distributive property. But when we multiply 2x times 3x, we get 6x squared. Okay? Try to internalize that, make it part of your long-term memory. Let's look at the 2x plus 3x again and consider some variations. Now, this is all addition again. See some minus signs in there, but you've learned that subtraction can be thought of as addition of an opposite. So subtraction is addition, it's based on addition. Notice the similarity in approach. We're going to get 3 different answers here, different than the 5x. We're going to approach it the same, and I'm not going to write out the distributive property here, but just try to keep in mind that 2x plus 3x is 5x. What about 2x minus 3x? Can you take a guess at what you think that would be? Well, 2 minus 3 is negative 1. So this would be negative 1x. Now, negative 1x is the same as negative x. I believe I showed you a proof of that back toward the end of the school year in the spring. If you multiply a number by negative 1, you get its opposite. So 2x minus 3x is negative 1x, which is negative x. And it kind of is intuitive again because 2 minus 3 is negative 1. What about negative 2x plus 3x? Well, you look at the negative 2 and the plus 3, that's now 1x. Negative 2 plus 3 is 1, so negative 2x plus 3x is 1x, which of course is the same as x. And finally, negative 2x minus 3x. Negative 2 minus 3 is negative 5x. So we recall that 2x plus 3x is 5x, but negative 2x minus 3x is negative 5x. And these kinds of things, if it seems a little foreign to you now, as you go through 7th and into 8th grade and into high school, these will become automatic. These are sort of some building block skills for algebra. What about if we, instead of taking 2x times 3x, what if we alter some of the signs here? Now notice the raised dot. These are all multiplications again. Remember that 2x times 3x was 6x squared. Well, all three of these are going to be similar, except we have to account for the sign. Here we have negative times positive, so it's going to be negative 6x squared. Negative 6x squared, right? The second one has the same result. Positive times negative is negative, so this one will be, again, negative 6x squared. But as you know, a negative times a negative is a positive. So if we have negative 2x times negative 3x, that'll be positive 6x squared, just like 2x times 3x is 6x squared. Negative 2x times negative 3x is also positive 6x squared. So that's just a little extension of the 2x times 3x. Let's now consider these. And notice I've introduced the letter y. In math, there's a fundamental assumption that within the same problem, if you have two appearances of the same letter, then they are the same number. Back with all of these that we started with, this x and this x are the same number. We must assume that they are. That's the rule of the game. This x and this x also the same number. But in a similar way, when we have two different letters, we have to assume that they're different numbers. Now, they could possibly be the same number, but we can't assume that. The x and the y here are different numbers. So what I want you to see with the first one is there is nothing we can do to that. It cannot be simplified. 2x plus 3y is not 5xy. It's not anything else other than what it is. The only thing we could do with 2x plus 3x is flip-flop the two things around the plus sign because addition is commutative. So it is equal to 3y plus 2x, but that's not simplifying it. And by the way, when I started back here, the directions to what we could have been doing here was simplify. It's easier or simpler to write 5x rather than 2x plus 3x. But this here, 2x plus 3y cannot be simplified. Because if we want to think in terms of the distributive property, there's nothing the same about these two terms here on either side of the plus sign. There's no x that we can pull outside the parentheses. There's no common factor if we want to use some vocabulary. So this cannot be simplified. Well, 2x times 3y can be simplified a little bit because, again, it's four numbers being multiplied together. It's 2 times 3 times x times y. And we can simplify the 2 times 3 to 6 and get 6xy. So that one actually can be simplified. 2x times 3y can be simplified to 6xy. But the 2x plus 3y, just can't add them. They are not what we call like terms. You can only add like terms. You can add numbers with numbers. 8 plus 3 is 11. You can always add to the numbers. You can add x's with x's, you can add y's with y's, but you cannot add x's with y's. Along that similar theme is an addition and a subtraction. You cannot add 2 and 3x. That cannot be simplified. Once again, because addition is commutative, we could write 2 plus 3x as 3x plus 2. And by the way, we usually do. Usually you'll see 3x plus 2 rather than 2 plus 3x. It's just a custom that we follow to put the x part first, and then just the number on the end. And in a similar way, 2 minus 3x cannot be simplified. We could rewrite this as negative 3x plus 2, because remember, we can think of subtracting 3x as adding negative 3x, put a plus sign here, and then flip the negative 3x and the 2 around the plus sign. But these cannot be simplified. You cannot add 3x plus 2. 3x plus 2 is not 5x. Please do not make that mistake. It's very easy to demonstrate, by the way, that 3x plus 2 is not 5x. But pick a value for x here. Let's say 4. Let's say x is 4. So 3x plus 2 would be 14, right? 3 times 4, 12 plus 2 is 14. But 5x, remember the x was 4, is 20. So 14 is not the same as 20. It simply doesn't work. However, if we're taking 3x and 2 and multiplying, then we can simplify. If you have to do 2 times 3x, you can think of that as 3 numbers being multiplied together. 2 times 3 times x. So you can simplify 2 times 3x as 6 times x, because you can do the 2 times 3. Just like if you were doing 2 times 3 times 4. That would be 6 times 4. You can do the 2 times 3 and times the third number. And then the rest of this is all sign rules, right? Negative 2 times negative 3x. Notice the raised dot here is indicating multiplication. Negative 2 times negative 3x. Negative times negative is positive. So this is also 6x. And the last two, look at what we have. Positive times negative and negative times positive. You know that that results in a negative. So each of these bottom two will be negative 6x. Okay? This is nothing more than the rules for multiplication that you learned in the 6th grade. Things like I just showed you, simplifying and sometimes not being able to simplify. These are some concepts and skills that will be a big part of 7th grade math. If you're a little intimidated by it now, don't worry. As we work through it, it'll become second nature. So now let's move on to the geometry. Here I have represented a rectangle. I've put little squares in each angle to indicate that they are right angles or 90-degree angles. And I've labeled the longer side L. When we talk about length and width, what's the difference? Well, the length is the longer side and the width is the shorter side. But here's a very important concept when we're talking about perimeter. It's very common in the English language to talk about the length and the width of a rectangle, or to say, for example, I have a 5 by 3 rectangle, a 5-inch by 3-inch rectangle. Talk like that. But there are 4 sides to a rectangle. So there are really 2 lengths and 2 widths. The sides that are across from each other are equal to each other. They're the same length. So we really have an L up there and a W over there as well. Okay? When you see a rectangle drawn in a textbook, however, a lot of the times you'll only have one of the lengths and one of the widths identified or labeled, but you have to realize the ones across are the same. So what about perimeter? Well, perimeter is you take the sides of the polygon and imagine breaking them apart, the line segments, and putting them end to end into one big line segment. And if you did that, you would find the length of that one big line segment by adding up the 4 pieces. Well, one piece has a length of L, another piece has a length of L, the third piece has a length of W, and the fourth uh, line segment has also a length of W. So we can think of this rectangle's perimeter as L plus W plus W. Now notice I didn't just go clockwise or counterclockwise here. I intentionally grouped together the two L's and the two W's, which I can do because when we're adding a bunch of numbers together, also, just like with multiplication, we can do it in any order or grouping that we want. Now, L plus L is 2L, right? Just this. Now you can see why I did some of that algebra. L is the same as 1L, so we have 1L plus 1L. That's 2L using the distributive property, or just using third grade knowledge. 5 plus 5 is 2 times 5. 6 plus 6 is 2 times 6. L plus L is 2 times L. So L plus L we will represent here as 2L plus W is 2W. And this is the classic formula for the perimeter of a rectangle. 2 times length plus 2 times width. 2L plus 2W. Now the distributive property allows us to also represent it this way. Each of these terms here, the 2L and the 2W, have a common factor of 2, which can be factored out outside of a parentheses. And we could say that it is equal to 2 times, in parentheses, L plus W. If you apply the distributive property here, 2 times L, 2L, plus 2 times W, 2W. So they are equivalent expressions. And now we come to the area of a rectangle, is length times width. And this is kind of a definition. It's a starting point. And in 6th grade, I used the area of a rectangle to show you how to multiply two fractions. At some point, I might review that a little bit, but we're just going to assume that the rectangle is the starting point and that the area of a rectangle being length times width is what we're going to build all the other formulas on. Now, originally, when I gave you this sheet, I started with the parallelogram. And it kind of makes sense to do that because the parallelogram is the general shape here. The rectangle and the square are both parallelograms. So area of a parallelogram equaling base times height could be considered a starting point, but also the rectangle can be considered the starting point. And by the way, the area of a rectangle is given as length times width, but we can also think of the length and the width as the base and the height. This L could be thought of as the base of the rectangle or parallelogram because it is a parallelogram, and the W as the height. And notice they meet at right angles. They're perpendicular. We've got the little right angle indicator here, which we know rectangles have. So area of a rectangle is length times width, which is the same as base times height. And we're going to actually develop the formula for the area of a parallelogram from the rectangle. And then we're going to develop the area for the formula of a triangle from the parallelogram and the rectangle. So it all comes back to the rectangle. Let's take a rectangle with sides of 3 inches and 2 inches. And I think you all know its perimeter. You can figure it out very quickly, right? The perimeter of that rectangle is 10 inches. You have to realize that this side here is also 3 inches, and this side here is also 2 inches. So you add, let me do it like this, 3 inches plus 3 inches plus 2 inches plus 2 inches. And again, you can see at this point, you can see why I covered 2x plus 3x is 5x. If we extend that a little bit, you can think of those inches as being an x. They work the same way, like an x. When you add 3 inches plus 3 inches, you get 6 inches. Just like if you added 3x plus 3x, you get 6x. 3 inches plus 3 inches is 6 inches, plus 2 more inches is 8 inches, plus 2 more inches is 10 inches. You could actually use the distributive property to show that if you'd like. You know, take the inches outside of a parentheses and then in the parentheses have 3 plus 3 plus 2 plus 2 and get the 10 inches. You can also go back to the formula that we just developed and say that this is 2 times 3 inches plus 2 times 2 inches. Right? 3 inches plus 3 inches is the same as 2 times 3 inches. So this is the length. So you got 2 times length plus 2 times width. 2 inches being the width. 2 times 3 inches is 6 inches. And 2 times 2 inches is 4 inches. And 6 inches plus 4 inches is 10 inches. Very simple. Okay? Now, the perimeter of anything, any polygon, triangle, rectangle, pentagon, hexagon, any kind of polygon, the perimeter is a distance around the outside, which is measured with line segments. And when we get to the circle and we're talking about its circumference, the circumference of a circle is its perimeter. So with the circle, we imagine we can take the circle, break it apart, and sort of stretch it all out to one big line segment. How long is it? That's the circumference or perimeter of a circle. And here we're thinking of laying those 4 line segments end to end to get one big line segment that's 10 inches long. Now that line segment is one-dimensional. It's just a distance. It's a length from one point to another, which happens to be 10 inches for this perimeter. But when we get to the concept of area, area cannot be measured with line segments. An inch is a line segment. A centimeter, a meter, a mile, a light year. No matter how big a distance is, it's a line segment. And it only has one dimension. Area is a two-dimensional measurement. You simply cannot measure the area of anything with a line segment like inches. You have to use squares. The square is the unit that we measure area with. And this diagram perfectly illustrates that. Here is the same 3-inch by 2-inch rectangle. You can clearly see that there are 6 squares that perfectly fill the inside with nothing short and nothing extra. 6 squares fill the inside surface of that rectangle. That's its area. Now, what is one of those squares? One of those squares is a square inch. It's a square where each side is 1 inch. See, across here, we have 3 inches. So this length here is 1 inch. This length is 1 inch. This length is 1 inch. Going up here, we have the width is 2 inches. This is 1 inch from here to here. And this is also 1 inch from here to here. All 6 of those squares have sides that are 1 inch long. Okay? And that's what we mean by a square inch. And there are 6 of them. Now let's look at the formula for the area of a rectangle. Of course, it's length times width or base times height. But the length, and this is the key thing, the length of this rectangle is not 3. It's 3 inches. And the width is not 2. It's 2 inches. So if we want to plug the length and width into the formula, we have to do 3 inches times 2 inches. And what I want you to think of now is 3x times 2x. Remember that? 3x times 2x was 6x squared because we saw it as 4 numbers being multiplied together. Well, we can do that here. We can think of each of those inches as being an x. So, you know, and you don't write this out probably, but just to illustrate why it works algebraically, we can think of 3 inches times 2 inches as being 3 times 2 times inch times inch, just like we did with 3x times 2x. 3 times 2, of course, is 6. And how do we abbreviate inches times inches? You know, 3 times 3 is 3 squared. inches times inches, we can write as inches squared. But how do we interpret this algebra here? And by the way, that is the answer to the question, what is the area of that rectangle? It's 6 inches squared, also known as square inches. So what we do is we take this algebraic notation, inches to the 2 power, or inches squared, and we relate that to one of these squares up here. I'll put an X through it, okay? So one of those squares, like I just put an X through it, that is 1 inch squared, okay? And there are 6 of them. So that's why the answer is 6 inches squared. We can also say 6 square inches. Either is correct. You can write it as 6 inches squared, or you can say that the answer is 6 square inches. And either way, we mean 6 of these squares perfectly fitting the inside of the rectangle. Okay. Now, here's a little secret about school math. It applies at the middle school level, probably even in the lower grades. And it definitely applies when you get to high school and you take a course called geometry. There's a little bit of a secret. Everybody who takes high school geometry first takes at least Algebra 1, sometimes Algebra 2. The high school math sequence can go either Algebra 1, Algebra 2, geometry, and then the higher courses, or it can go Algebra 1, geometry, and then algebra, depending on the school you go to, the level you're in, and so on. But either way, when you're taking high school geometry, you've already had some high school algebra. And here's the secret. You're going to be asked to apply the algebra that you already learned when you're in the geometry class. The focus of the course is obviously going to be geometry, but you'll have to use algebra to work out problems and to get answers. And by the way, what I just said about you use algebra in geometry is also true in calculus. Some of you know that some people, when they get to 12th grade in high school, they take a course called calculus. Well, you're still doing algebra to ultimately answer a question. You do the calculus first, then the algebra to answer the question. Well, here's a pretty simple, I think, all of you should be able to handle this geometry word problem. But I'm going to show you how we can use a little bit of algebra to solve it. So we have a rectangle that has a perimeter of 17 inches. And its length is 5 inches. Now remember what I said though. This is the way anybody would word this problem, very similar to this. The question is, what is its width? Notice I said its length. Sounds like there's only one of them, but there are really two. You have to realize that when we talk about the length of a rectangle, there are really two of them. So think about this problem. You should be able to do it mentally. It's pretty easy. I'll give you a clue. The answer is not a whole number. The width is not a whole number of inches. Okay? Pause the video if you need to. I'd like you to get an answer before I continue. So maybe you've paused. Did you figure out that the width is 3.5 inches or 3.5 inches? And as I go through the explanation, think about how you did it, and probably you can see how your method relates to mine. Probably what a lot of you would have done first is subtract 10 from the 17. Did you do that? Well, why would you subtract 10? Because there were two lengths. 5 inches plus the other length is 5 inches. That's 10 inches. Subtract that from the 17 inches of the perimeter. That gives you 7 inches. Now, the two sides remaining are both called widths. They have to be the same length. Both widths are the same, and they have to add up to 7 inches. So each one is 3.5 inches. Here's a diagram. This is the rectangle that I was talking about. 5 inches by 3.5 inches, right? Here's the length of 5 inches. There's another length up here of 5 inches. So that's 10. You subtract the 10 from the 17 here. 3.5 inches for that width and 3.5 inches for the other width. The perimeter of this rectangle is 17 inches. Okay. How do we approach this problem algebraically? Well, The perimeter is 2 times the length plus 2 times the width. This is the formula for the perimeter of a rectangle. Now we can plug numbers in at this point. We can plug 2 numbers in. There are 3 that are unknown in the formula. There's the P, the L, and the W. 3 letters representing numbers. We know 2 of them. That's what allows us to solve. The perimeter is 17 inches. So we can substitute 17 inches for the P. And the length is 5 inches. So we can substitute 5 inches for the length. That's all I did in writing this line here. Now, remember earlier I kind of covered this? What's 2 times 5 inches? It's 10 inches. There's the 10 inches, right? That most of you probably thought about. That you have to sort of figure out that 2 sides total, the 2 lengths total 10 inches, plus the 2W, and the W, of course, is the unknown. You should at this point recognize this last line as a 2-step algebra equation, where the unknown is W. How are we going to approach this 2-step algebra equation? Well, aren't we going to subtract 10 inches from each side first? And you probably did this mentally. You weren't thinking about this algebraic notation when you came up with the 3.5 inches, but you probably did 17 minus 10, or technically 17 inches minus 10 inches. So if we subtract 10 inches from each side here, minus 10 inches, minus 10 inches, and you see how those 2-step algebra equations that we learned can be applied and used to solve problems. That's what math is all about. It's solving problems. And the algebra is a tool that helps us to do that. So 17 inches minus 10 inches is 7 inches. And then these 10s cancel, which is they add to 0. That's why we subtracted 10 inches from each side. So the only thing left on the right side is the 2W. I'm kind of running out of room here, but what's the final step? Divide each side by 2, right? Divide each side by 2. The 2's cancel on the right side, leaving the W. And 7 inches divided by 2 is 3.5 inches, or 3.5 inches. I see that we're at more than 37 minutes. What I'm going to do is make this 3rd and final summer installment go into another video, just so you can take a break. Maybe even watch part 2 another day. It's up to you. But I'm gonna stop now and then finish with a part 2.